In this procedure,
A motor draws more current, typically 6 times more, at startup than when it is operating at its rated full load speed. This is called the inrush current. Therefore, if a fuse is chosen based on the full load current rating for a motor, the fuse will blow each time the motor starts. This is why time delay fuses are commonly used in motor starting applications. A time delay fuse actually has two different elements, an instantaneous element and a time delay or overload element. The time delay element is a thermal element that will melt and open after an excessive current is present past its time delay. The time delay element is typically designed to be at the same hold current rating as the overall fuse rating. It can handle the increased starting current of the motor for a duration, typically 10 seconds. Therefore, if the fuse is rated for 100 amps, the current must be below this rating before the time delay expires or the thermal element melts and opens. The instantaneous element is designed to blow at a current level that is about 5 times higher than the hold current rating of the time delay element. This level is only reached if a short circuit occurs. In this case, it will blow immediately. The time delay fuse can handle the increased starting current of the motor and will allow the motor to start. However, if the high current continues past the time delay period, the fuse will blow. Time delay fuses are larger than most regular fuses because of their dual element construction. They are also labeled so that you can easily identify them. Describe 3 important factors to consider with overcurrent protection devices. An overloaded motor or a short circuit can cause an overcurrent. Steps must be taken to make sure that the motor control circuit has protection for both types of overcurrent. When selecting an overcurrent protection device for a motor control circuit, consider 3 factors. They are rated full load current, conductor ampacity, locked rotor current. The full load current is the current that a motor draws when it is fully loaded and operating at its rated speed. The full load current determines the control circuit's running overload current rating. The NEC states that the running overcurrent protection should meet but not exceed 125% of the motor's rated full load current for motors with a rated ambient temperature of 40 degrees Celsius and a service factor of 1 and 1500ths or higher. For example, the current rating would be 31 and 2500ths amps for the time delay thermal units used as running overload protection for a motor that has a rated full load current of 25 amps. Ampacity is the maximum current carrying capacity of a conductor. Factors that determine the ampacity of a conductor include the gauge of the wire, the type of insulation, and the number of conductors in a conduit. The NEC says that the running overload protection cannot exceed the ampacity of the conductors supplying the motor. The locked rotor current is the high inrush current drawn by a motor when it is first turned on. It is called locked rotor current because if the rotor was locked in place, this is the amount of current the motor would draw. The overcurrent device must be able to handle this high inrush current for a short period to allow the motor to accelerate to its rated full load speed. If the overcurrent protection rated for 125% of full load current is not enough to allow the motor to accelerate to its full load speed, the NEC allows you to choose a higher rated device. However, it cannot be higher than 140% of the full load current.
Size circuit protection. In this procedure, you will select the circuit protection for various applications given the operating conditions. You will use this skill in the field when selecting protection devices. Click on the equipment to view the
The stator of a three-phase motor is made up of three separate sets of windings, one set for each phase of power fed to the motor. Since the windings are identical, the three-phase motor does not depend on the windings themselves to produce the rotating magnetic field, like the single-phase motors. The three phases fed to the stator windings are already 120 degrees apart. The phase difference of the three-phase power itself is what produces the rotating magnetic field for a three-phase motor. The stator windings are grouped together to form magnetic poles from the magnetic fields that generate when energized. The rotating magnetic field is developed using the three-phase power. Each point, 1 through 6, represents a different point in time during an electrical cycle. As you can see, at each point only 2 of the 3 phases have current flowing. Also, the 2 phases that have current flow change at each point of the cycle. This step-by-step demonstration will take you through a complete cycle and show you how 3-phase power generates rotation in a motor. Point 1. At point 1, a positive current flows in the windings connected to phase A, and a negative current flows in the windings connected to phase C, which causes a magnetic field to develop between A1 and C1 and between A2 and C2. Because no current flows in the windings connected to phase B, poles B1 and B2 are not magnetized. Point 2. At point 2, the current in phase A is 0, which means that poles A1 and A2 are not magnetized. However, positive current flows in the windings connected to phase B, while negative current still flows in the windings connected to phase C, which creates a magnetic field between poles B1 and C1 and between poles B2 and C2. Point 3. At point 3, the current in phase C is 0, which means poles C1 and C2 are not magnetized. The current in phase A is negative, and the current in phase B is still positive. This creates a magnetic field between poles A1 and B1 and between poles A2 and B2. Point 4. At point 4, poles B1 and B2 are not magnetized, while a magnetic field exists between poles A1 and C1 and between A2 and C2. Point 5. At point 5, poles A1 and A2 are not magnetized, while a magnetic field exists between poles B1 and C1 and between B2 and C2. Point 6. At point 6, poles C1 and C2 are not magnetized, while a magnetic field exists between poles A1 and B2 and between A2 and B2. Point 7. At point 7, the cycle begins again. As you can see, the magnetic field pattern continues to rotate between 2 sets of poles as the 3 phases continue to cycle. Therefore, if a rotor is placed inside this rotating magnetic field, the field will cause the rotor to rotate, just like the rotor on a single-phase motor. The squirrel cage motor gets its name from the design of its rotor. The rotor of a squirrel cage induction motor consists of heavy copper bars which are connected together at each end by end rings, usually made of copper or brass. This forms a cage around an iron core. The rotating magnetic field created by the stator acts on the copper bars and causes the rotor to rotate. In addition, since we are focusing on induction motors, we know that there will be a certain amount of slip between the speed of the rotor and the synchronous speed. The average range of slip for squirrel cage induction motors is 2% to 6%.
The NEC Article 430 requires that certain operating data be supplied on the nameplate of a motor. In many cases, the manufacturers actually provide more than the required data. The information on a motor's nameplate contains all of the necessary performance data for that motor. The typical items found on a motor's nameplate are manufacturer, frame, horsepower, voltage, amps, speed, frequency, service factor, phases, ambient temperature, insulation class, and NEMA code. Each manufacturer uses their own system for identifying motors by catalog number, part number, model number, etc. Knowing the manufacturer will make the task of pricing and replacing a motor much easier. Each manufacturer uses the frame or FR listing designates frame size as identified by NEMA. This listing indicates the physical characteristics of the motor such as physical size, construction, and dimensions. Having the frame sizes standardized allows you to replace a motor from one manufacturer with a motor of the same frame size from another manufacturer. A common frame size for small motors is 56. Electric motors are commonly rated in horsepower or HP in the United States and in kilowatts or kW in most other countries. This listing tells you the amount of mechanical energy the motor can provide. The voltage listing, volts, indicates the voltage that the motor is designed to use. Some motors can be configured to operate on two different voltages. These motors will show dual voltage ratings such as 120, 240 volts AC. The current listing, usually designated either with an A or with amp, indicates the full load current rating for the motor. If the motor is a dual voltage motor, there will be two current ratings listed, one for each operating voltage. This current rating is one of the factors that determines the overcurrent protection for the motor. The speed listing, RPM or revolutions per minute, indicates the speed at which the motor runs when delivering its rated output power, horsepower or kilowatts. However, the speed indicated is not the synchronous speed, but the actual speed of the rotor due to slip. The frequency listing, or hertz, indicates the frequency of the power the motor uses. In the U.S., the frequency is 60 hertz. In many other countries, the frequency is 50 hertz. The service factor, or SF, is used to determine how much output power a motor can safely produce above its rated horsepower. The phase listing, or pH, indicates the number of phases the power source should have. The phase listing will either be 1 for single-phase motors, 3 for three-phase motors, or DC for direct current motors. The ambient temperature is the temperature of the air surrounding an operating motor. The ambient temperature rating, AMB or rating, is the maximum ambient temperature that the motor can tolerate before the insulation of the windings begins to break down and the lubrication dries out. Operating the motor above its rated ambient temperature will eventually lead to motor failure. A high ambient temperature means a much higher temperature inside the motor. Insulation for motors is ranked in different classes. 4 common classes are listed. Class A can withstand temperatures up to 105 degrees Celsius. Class B insulation is rated for temperatures up to 130 degrees Celsius. Class F insulation is rated for temperatures up to 155 degrees Celsius. Class H is rated for temperatures up to 180 degrees Celsius. The code listing is a NEMA designation used to show the locked rotor rating for the motor. The locked rotor rating is in kilovolt amperes. Many dual-voltage motors include connection diagrams on their nameplates that show how to connect the motor leads to operate on either the low voltage or the high voltage. Another common listing is the efficiency, or EFF rating. The higher the efficiency rating, the lower the operating cost of the motor. Define service factor and explain its importance. Some motors can be operated above their rated output power without damaging the motor. The service factor represents the margin of safety for operating a motor above its rated output power. For example, a 10 horsepower motor with a service factor of 1.15 can produce 115% of its rated horsepower, or 11.5 horsepower. Typical service factors include 1, 1.15, 1.25, and 1.35. The service factor is considered when choosing an overload relay for a motor. Note: if a motor has no service factor listed on its nameplate, you must assume that the service factor is 1. This means that the motor should not be operated above its rated output power. Connect a dual-voltage, 3-phase motor for low-voltage operation. In this procedure, you will connect a dual-voltage, 3-phase motor to operate on the low voltage. You will connect the motor according to the connection diagram that is included on the motor nameplate. You will then operate the motor and verify some of its performance data for the low voltage configuration. Select Simulator or Hardware to perform this procedure. Once you have completed one, you may go through the other. A dual voltage motor should be operated on the higher voltage rating so that the motor will draw less current. The reason behind this is that when the motor windings are connected in series for high voltage, the inductive reactance of the motor is higher than when the windings are connected in parallel. The higher inductive reactance results in a lower current draw. Lower current draw allows the use of smaller wires to feed the motor, which reduces line losses, increases efficiency, and reduces operating costs. Connect a dual voltage 3-phase motor for high voltage operation. In this procedure, you will connect a dual voltage 3-phase motor to operate on the higher voltage. You will connect the motor according to the connection diagram that is included on the motor nameplate. However, because you only have 208 volts AC available, you will not be able to operate the motor in this configuration. Select Simulator or Hardware to perform this procedure. Once you have completed one, you may go through the other.